egiten cap.
Buenos días a todas, a todos. Se va a proceder a dar comienzo al solemne acto de investidura del grado de doctor Honoris Causa por la Universidad de Zaragoza de don Alan Gelfand. Secretario General, por favor, lege studi generalis civitatis Caesar Augustane Senatus Consultum.
Acuerdo de 25 de junio de 2025 del Consejo de Gobierno de la Universidad de Zaragoza, por el que se nombra doctor honoris causa a don Alan Gelfand. En virtud de lo dispuesto en los artículos 51 y 117 de los Estatutos de la Universidad y de conformidad con el reglamento de nombramiento de los doctores honoris causa, a propuesta del Departamento de Métodos Estadísticos, del Departamento de Economía Aplicada y del Instituto Universitario de Matemáticas y Aplicaciones, y a la vista de los informes favorables de la Junta Consultiva Académica y de la Comisión de Doctorado, el Consejo de Gobierno acuerda conceder la distinción de doctor honoris causa por la Universidad de Zaragoza a don Alan Gelfand.
Por favor, madrina, padrino del candidato, ite accessite candidatum.
Don Alan Gelfand.
Sedete. Pronuntietur a patronis laus candidati.
Profesora doctora doña Ana Carmen Cebrián Guajardo y doctor don Gerardo Sanz Saiz.
Con la venia de la rectora magnífica de la Universidad de Zaragoza, claustro togado, autoridades, miembros de la comunidad universitaria, familiares, señoras y señores. Es un verdadero honor para el profesor Gerardo Sanz y para mí apadrinar al profesor Alan Gelfand en su nombramiento como doctor honoris causa por la Universidad de Zaragoza. Y no solo para nosotros, sino también para los tres proponentes, los departamentos de métodos estadísticos, el de economía aplicada y el Instituto Universitario de Matemáticas y sus aplicaciones, así como para la Facultad de Ciencias, que también apoyó este reconocimiento. Dado que es un placer contar hoy con la presencia de investigadores internacionales, permítanme continuar el resto del elogio en inglés. According to the regulations governing the awarding of the Doctor Honoris Causa degree by the University of Zaragoza, this distinction is conferred upon individuals who have achieved exceptional prestige in research and who embody universal values. In addition, the candidate's connection with the University of Zaragoza is also considered. And honestly, I cannot think of anyone who fulfills each and every one of these requirements better than Professor Gelfand. To avoid any doubt, we can follow the usual mathematical procedure and formulate this as a theorem. We have three hypotheses: international prestige in research, embodiment of universal values, and close connection with the University of Zaragoza. And if we demonstrate this hypothesis, we reach the conclusion that Professor Gelfand is the perfect candidate to be awarded Doctor Honoris Causa by the University of Zaragoza. The demonstration of this hypothesis is irrefutable, as we'll show. Hypothesis 1, scientific prestige. I must say that proving this thesis is very easy. However, doing so in just a few minutes is almost impossible, since it's difficult to summarize in such a short time the innumerable merits of his academic career. Therefore, what follows is only a brief overview. Born in New York, Alan Gelfand earned his undergraduate degree in mathematics at the City College of New York. He obtained his PhD in statistics from Stanford University under the supervision of Professor Herbert Solomon. He began his career at the University of Connecticut, where he worked for more than 30 years. In 2002, he joined Duke University, ranked 6th among USA universities, where he was appointed James B. Duke Professor of Statistical Science, the most prestigious academic position at that institution. His name will forever be linked to one of the most significant milestones in recent statistical history, the use of Monte Carlo Markov chains methods in the context of Bayesian analysis. In 1990, together with Professor Adrian Smith, Professor Gelfand published the article Sampling-Based Approaches to Calculating Marginal Densities in the Journal of the American Statistical Association, one of the most prestigious statistical journals. This article marked a turning point in modern statistical inference, as it made it possible to tackle problems that had previously been virtually intractable. What had been purely theoretical, thanks to Professor Gelfand, became a practical, applicable, and useful technique. That article has been cited more than 10,500 times. As many Bayesian researchers say, give sampling, which is a key algorithm in Bayesian research, should be referred to as Gelfand's sampling. Since then, he has made significant contributions to multiple areas, most notably Bayesian hierarchical modeling, spatial statistics, and spatiotemporal modeling. His scientific productivity is extraordinary. He has published more than 350 articles in academic journals, 10 books and monographs, and supervised dozens of doctoral theses. His influence has been fundamental in the spread of Bayesian analysis. His book, Hierarchical Modeling and Analysis for Spatial Data, co-authored with Professors Banerjee and Carlin, is considered one of the Bibles of Bayesian modeling, and its third edition has just been published. Professor Gelfand has received many distinctions for his research. To name just a few, the Wilkes Memorial Award, Distinguished Research Medal from the American Statistical Association, elected fellowship of the International Statistical Institute, the American Statistical Association, and the International Society for Bayesian Analysis, where he also served as elected president, and more recently, the Chernoff Excellence Statistics Award. He was recognized as the 10th most cited mathematical scientist in the world for the period 1991 and 2001, and currently ranks amongst the world's top mathematicians in the Research.com ranking. Again, please note that this is only a brief overview, as his list of awards is extensive. Hypothesis 2, embodiment of universal values. As we have just established, Professor Gelfand's research has made an essential contribution to the theoretical foundations of Bayesian analysis, but his influence extends well beyond this area. He has devoted an important part of his work to developing Bayesian applications to address problems of social interest, especially in environmental sciences, health, pollution studies, and biodiversity. He has also worked on climate applications, developing models of great utility in monitoring climate change. There is no doubt that his research has helped to improve the world and the society where we live. His universal values are further reflected in his generous commitment to mentoring young researchers and his extensive collaborations with diverse research groups. He has supervised more than 50 doctoral students, and in the words of one of them, he is what might be regarded as the definite model of a thesis advisor. He has also established research collaborations across the world, and all this with a generosity that has fostered not only professional relationships, but also lasting friendships. Proof of this is the presence here today of many leading international Bayesian statisticians who have traveled from different parts of Spain, from Rome, Southampton, and even across the Atlantic, from Washington, Texas, California, and North Carolina. All are gathered here in Zaragoza to celebrate with him the conferral of his degree. For me, this is irrefutable evidence of the great impact Alan has had on all of them, both as a researcher, but also as a person. Hypothesis 3, connection with the University of Zaragoza. Professor Gelfand's collaboration with this university began in 2012, first with Professors Manuel Salvador, María Asunción Beamonte, and Pilar Gargallo from the Economía Aplicada department, and thereafter with the Faculty of Science. Since 2014, thanks to Professor María Asunción Beamonte, he has been part of the group Modelos Estocásticos, led by Professor Sanz. His influence on this university is undeniable. Dennis Linley, one of the great promoters of Bayesianism in the 20th century, once said, "Inside every non-Bayesian, there is a Bayesian struggling to get out." Without a doubt, Professor Gelfand has brought out the Bayesian in many researches at the University of Zaragoza, including myself, of course. The result is that, thanks to his influence, there is now a significant node of Bayesian statisticians at this university. Regarding the university's projection abroad, Professor Gelfand's collaborations with the University of Zaragoza have used data from Spain and from this region, Aragon, so that through his numerous publications and keynote talks, he has promoted both the region and the university worldwide. Professor Gelfand visits regularly our university, and at this point I must express the honor and pleasure it is to work with Alan. And I'm sure that Jesus Assin, Jorge Castillo, and other researchers here will agree with me. In each and every meeting with him, we learn something. In our work discussions, new ideas always emerge, of course proposed by him, but I would even say that his presence sparks better ideas from the rest of the team, the Zaragoza team, as he calls us. Moreover, he fosters a collaborative environment where all ideas are heard, not imposing hierarchies, even though his position would certainly allow it. This accessibility, despite his many achievements, makes it easy to forget what an honor and privilege it is to work with one of the world's leading mathematicians. It's therefore valuable to be reminded of this. I recall that after publishing our first article with him, one colleague congratulated me on that publication, and I said, "Yes, we are very happy. It's my first article in this prestigious journal." And he replied, "Well, actually, I wasn't congratulating you for the journal, but for having published with Alan Gelfand." And he was right. The true honor of that work was having worked with Alan, and it remains so. In every project we undertake together, it's a privilege for us to work with him. With all this, we have proven beyond any doubt the three hypotheses necessary to reach the conclusion we wanted to demonstrate: that Professor Gelfand is the perfect candidate to be awarded Doctor Honoris Causa by the University of Zaragoza. Thus, we can only conclude this laudatio, dear Professor Gelfand, by saying thank you. Thank you for your valuable contributions to science, to mathematics, to statistics, and to Bayesian analysis. Thank you for your support and generosity toward us, toward the Modelos Estocásticos group, and toward the entire University of Zaragoza. And thank you for accepting your appointment as Doctor Honoris Causa by this university, as a token of recognition for your contributions. In short, dear Professor Gelfand, we warmly welcome you as a new Ilustrado of our university, which from now on is also your university.
Debate. Conceditisne ut Alan Gelfand honoris causa munia doctoris induatur. Autoritate mi concessa legibus regni. Et stadi generalis civitatis Caesar Augustane tibi confero gradum doctoris honoris causa. Patroni insignibus doctoralibus te vestient. Et eorum significationem explicabunt. Sedete.
Don Alan Gelfand, pilium, sí. No, tenéis que el pilium. Tenéis que hacerlo.
Non sol esplendore ceteros praecedas, sed poetiam tanquam minervae caside, ad certamen munidios sis. En librum napetum descientarum arcanim resedes. E clausum uteadem pro cocorteat intimo pectore custodias. Dotivi facultatem legendi e interpretandi.
Lévate. Lege promissum novo doctori.
Promitis observare et adimplere omnia et singula quae secuntur. Primo, semper et ubicunque fueris jura et privilegia honorem studii generali civitatis et Augustanae conservabis, et semper id adjuvabis favorem auxilium et consilium prestabis, in factis et negotis universitatis quotis fueris requisitus?
Sic promito et sic volo.
Accipium promissum tuum. Studium generale civitatis Caesar Augustanae testises etiudis erit si fidem decederes.
No, ya está.
¿Y ahora tú le dices? No. Espera.
Don Alan Gelfand.
Sí. Puede ocupar la cátedra el doctor Don Alan Gelfand.
directora magnífica, sí, del equipo tal, miembros del claustro, profesores, alumnos, señoras y señores, este discurso no es técnica, necesita solo ideas de modelos, de datos y inferencia, pero no un nivel muy elevado. Quiero presentar todo en español, pero no puedo hacerlo para 30 minutos, no puedo. Pero la versión en el librito es muy fácil de leer, creo, y así ahora cambio a inglés. Perdón. So, this title is, again, something that I suspect many people don't know very much about. So, just to start, the idea is to tell you that even if you don't know much about statistics, and you certainly probably don't know much about Bayesian statistics, I'm going to try to tell you a little story about the evolution of Bayesian statistics in the last maybe 30 or 40 years. So that's what we're going to do, and I hope you will be able to stay awake. To those who are knowledgeable, I have to ask you to excuse any omissions and put up with my subjective view. I think everybody knows about the importance of statistics these days, and perhaps everybody's had some exposure to statistics these days. Sometimes it's negative. In English we say sadistics rather than statistics, but in any event, we also know about many abuses committed in the words of statistics. The famous book, which was Liars, More Liars, and Statisticians. So the books are out there, but I think it's also true that in the 21st century, it's impossible to do serious research without using data and without using statistics to support your conclusions. So also, I think everybody knows the words big data and data science, and so again, we are clearly surrounded by un montón de datos, and it's clear that we have to, we have to work with them, we have to understand them, we have to appreciate the complex processes that they are trying to explain, and so statistics is clearly important. The range of applications, I'm not even going to recite them, but they are everywhere, and you don't have to be very precise about the field in order to know that. And the range of problems is very broad because it depends, again, on what you are interested in studying. And for me, the last ones, the spatial and spatiotemporal data questions are maybe the most interesting, and we'll get to a little bit of that later. So where does Bayesian inference come from? Well, look, it's, in some sense, it started as a rebellious paradigm. And what I mean by that is the classical paradigm was there for forever. And I'm not going to say that much more, except that the origins of it are rather simple, from the Reverend Thomas Bayes, who was a philosopher and a mathematician, and presented something called Bayes' theorem in the 1750s. He died before it was published, so it was submitted by a friend of his, Richard Price, and that humble beginning is where we start. So Bayes was thinking in terms of conditional ideas. He was thinking in terms of, okay, how does the chance of an event A change if I tell you the event B occurred? That's the question he was asking. And without getting much into the probability of it, there's just a simple relationship, which is in the third blue arrow, and that third blue arrow enables you to turn around what looks like P of A given B, the chance of A given B happening, from the chance of B happening given A happened. And I'm not going to do a numerical example, there's one in the librito, but pretty simple. And I think the real idea is, how does this become an inference paradigm? And the idea here is that we replace events by random variables. We do this all the time. We are always interested in randomness. We are always interested in uncertainty. And so using this, we can show that we obtain f of x given y through the terms on the right-hand side in the second bullet. And now what I'd like you to do is say, well, all right, in any problem that we come up with, we have both data and we have unknowns. The data is what we have to work with, and the unknowns we'd like to use to, we'd like to learn something about. They are going to be describing the process that we're trying to understand better. And so what we'd like to do is use the third bullet here, the third bullet being this one, f of unknowns given data. And what we're trying to do is infer about what we don't know, the unknowns, given what we have seen. And this seems perfectly natural. This is the way we live life every day. You get up in the morning and you know what you know, and you make decisions about, okay, what's the temperature, what am I going to wear, what food am I going to buy? I mean, we all live life, I think, trying to decide what we don't know given what we have observed. So it seems completely natural. If I write it a little more technically, and I apologize, this may be the last really technical bit here, but what we're trying to do is describe a joint distribution between two sources of information. One are the unknowns that I just described, and the other is the data that we have collected. And we can write it using the central term. Using the central term here, we can write it as data given unknowns times unknowns. And so what this sort of says is, this is the way life is. Unknowns are selected by Mother Nature or whoever your favorite deity is. Mother Nature does that, and then after those unknowns are selected, then the data is captured given those unknowns. And so that's what the middle is referring to, and that's the generative version of this. But the term on the right side is what we really care about. That's the inferential term. It shows what we call belief revision. It revises the inference on what we don't know given what we've seen. In other words, we started with unknowns, f unknowns, but now we have a better idea from f of unknowns given data. So it has informed us about the things we want to learn about. What about classical inference, which again has dominated for more than 100 years and probably still dominates today? Bayes is moving forward at a fast pace, but there's no doubt that the classical or frequentist approach dominates. So the classical approach asks you to think about that term, data given unknowns. Try to think about are one is called a parameter. One is called a parameter. A parameter is something like a regression coefficient or a correlation or a variance, words you've probably seen or heard somewhere. And they are artificial. They're not real because they're part of the model that you specify. And so when we try to learn about them, we do estimation, but we have to acknowledge again that they're somewhat artificial. The other type of unknown is an observation. It's in something that is in the real data space. It's something we could have observed. In fact, like I wrote here, it could be a temperature, a property value, a birth weight. It could be any sort of thing that we could observe. And those are real. So there's nothing artificial about those. And so from my point of view, I'm a predictivist, and in that regard, I like to think about model performance exclusively in the space of data. In other words, what we can see, what we can observe, and I'm not so interested in estimation. I mean, I do it, it's part of, model fitting, model inference, but in any event. So again, this is just to probably summarize everything that I've already said, but the classical approach, again, looks at this likelihood, the f of data given unknowns, and it uses statistics, functions of the data, to try to tell us about the unknowns. And the functions of the data that they use, the statistics, usually have distributions that are not available to us. They're too ugly, they're too messy, they're too technical. And so what we do is often move to approximations in the form of asymptotics. And asymptotics for me are, again, something I don't have much interest in. And the reason? Because asymptotics requires data that you're never going to see. Something in the future, more data than you could ever hope to collect. And so how do you know if you're doing well enough with the data that you have? So I don't really care for it, and again, Bayesian inference doesn't require you to do that. Also, the inference is limited with classical statistics because of the fact that you might get an estimate of a point, you might get an estimate of a variance, you might get an estimate of an interval for the unknown, but that's about it. Whereas from the Bayesian point of view, you get a whole, what we call posterior distribution. You get a whole distribution to tell you about what you want to know, what's unknown. So that means you can have any point estimate you want, mean, median, mode, you've heard these words, any uncertainty you want, variances, ranges, making probability statements about where this unknown might fall, all sorts of things that are, enable you to do what we call full inference. And the best thing is, with a Bayesian model, the inference is exact. You don't have to worry about asymptotics. Under the model you propose, the inference you get is exact. And for me, that's very satisfying. I don't have to worry about what I might never see, probably will never see, especially at my age. I know I'm never going to see. But anyway, so therefore you ask the question, why didn't Bayesian inference emerge as the dominant paradigm after all these words that I've been offering? And the interesting point here is that if you go back to the earlier slide, you have this question of F unknowns, which is called the prior distribution, and the prior distribution is clearly going to be subjective. You may think a priori about what you don't know differently from the way I might think a priori about what you don't know. And so if that's the case, if we have two different priors, we're going to wind up with two different posteriors. We're going to wind up with different inference. If we wind up with different inference, how can that be good science? How can you justify something like that? So that's been the criticism immediately of the Bayesian paradigm. It turns out this is not the serious issue. This is not the serious issue. As I show here, we maybe have useful information about these unknowns from just the science we've studied. We may have previous data on the process which has revealed where they're likely to be. We know certain values of these unknowns could give us data that we would never ever see in the real world. And we even have mechanisms like elicitation to use experts to try to tell us a little bit about these unknowns. So altogether, we actually have tools to try to do this, but in fact, we don't even do this much anymore. We don't really do this. What we do is, as it says in the first bullet, let the data do the talking. So we're going to assume this prior doesn't carry much information. We're going to assume this prior is just essentially non-informative, is what we call it, and there are different ways to describe it. But the important thing is we then kind of put all the emphasis on whatever information is in the data, and the data, therefore, we hope will carry the day in terms of the inference we're going to use or extract from the posterior. So that's the story. I have a list of names here, some influential Bayesians. I'm not going to read all the names, but these are, and again, I can only apologize for omissions, but these are some of the people who have been very influential, and the last bullet are those who are very influential nowadays. And of course, there are a lot of Bayesians in Spain. Spain has a long tradition as well, and I just highlight again some of those names here, and again I can only apologize for some omissions, but the point really is a lot of this work started in Valencia, and Valencia is still probably the home of Bayesian inference, not only in Spain but perhaps in the world. And so it's again it's very special to connect with all the Bayesians from Valencia, and again, I'm not going to read all the names. So let me go back a step. Dennis Lindley, one of the founding fathers of Bayesian inference, and I mentioned a few other names there, But he forecasted that the 21st century would be a Bayesian century because of the inferential attractiveness. What I just described earlier about how it's a nice way to infer about what you don't know given what you've seen. It seems, completely attractive. But the answer is Bayesian inference has risen to be more and more utilized, not because of that, but because of solving the computational problem. The computational problem is what I'm going to spend 2 slides on, and I apologize if it's going to get a little bit technical, but not much. So let's go back to this basic relationship that we had earlier, f of unknowns given data, and you can see that what we're missing here is this guy, f of data. We don't have f of data. In other words, I don't know what that is. I can tell you what I assume a priori. I can tell you how the data arises from the models. I can't really tell you this. In fact, in order to get this, I have to do integration. I have to integrate over the space of all unknowns. And as you have more and more unknowns, which happens with more and more complex processes that we study, you wind up having to do really complex integration. So that killed Bayes for a long time until we had a nice breakthrough. So Adrian Smith and I were able to, fortunately, come up with a seminal paper that broke through and enabled us to do this inference using something called Gibbs sampling and Markov chain Monte Carlo, which Anna Carmen referred to earlier. And the result of that is this has become the most prominent tool for implementing Bayesian inference. And again, I'm not going to say much about this, except that it did essentially create the rise of Bayesian inference in the 21st century. The basic idea, though, is not hard to understand. Basic idea simply says that because we can't do integration, what's an alternative? And the alternative is sampling. The sampling is what we do all the time. That's what statistics is all about. You sample a population in order to learn about the population. And the more you sample, the better you learn about the population. And so the idea is, can we sample this distribution that we really need integration to get explicitly? And the answer is yes. The answer is what Markov chain Monte Carlo produces. And essentially what it does is, in a slightly unexpected way, it gets the stationary distribution of a Markov chain to be exactly the distribution you want. And I'm not going to say anything more than that because those words already might have put you to sleep. But in any event, that's what we do. And the other thing that's in the last bullet is, at the time we did this work, it was very fortunate because inexpensive, high-speed computing started to become available. Now we take all that for granted. Now we don't think much about it. What you can do on a laptop is astonishing. And if you have a selection of nodes, in a university setting, for example, what you can compute nowadays is beyond what's believable. Just think about what's on your phone, what you can do with your phone. So it's obvious that the availability of high-speed computation joined with this idea really facilitated it. So what it did was it kind of opened the door. It liberated people from having to deal with what was available through asymptotics. It sort of said to people, no. Focus on the process. Focus on the modeling that you're interested in. You don't have to worry about whether somebody's already done this before. You just do what you want and you implement the fitting of the model using this Markov chain Monte Carlo. And of course what happened is models got bigger and bigger. More and more data got collected, and all of a sudden, you had to start to think about whether your model is as big as an elephant. And if that's the case, have you really explained anything? And so as a result, it's a wonderful gift, but it has to be used with caution. And following up on that, other variants have emerged, like integrated nested Laplace approximation, and ABC, approximate Bayesian computation, and variational Bayes. And some of these can be better for some problems, but I would still say at present Gibbs sampling and MCMC are still the most widely used tool in this new Bayesian era. Okay, I have to say a few words about hierarchical modeling, because hierarchical modeling is, again, where all of this really comes into play. Because all of this really comes into play from this top equation here, where I've added another level. In other words, before I had just data given unknowns, but now I have data given process and unknowns, and then I have process given unknowns, and then the unknowns. And the idea here is I want to put in this process that I want to learn about. And I'm not even going to tell you what process this is. This could be as complicated as you want it to be. Depends what you're studying. Are you studying something in biology, something in sociology, something in economics, something in, whatever field you're looking at, you have a process there. You don't know the process, but you can sort of put a model for the process, and you want to learn about the unknowns that drive the process. And so what we have here are sort of unknowns that drive the process, and then unknowns that drive the data given the process. And so now we want to learn about two sets of unknowns, and this gives us a very nice way of thinking about building models, and it's called hierarchical modeling. And again, I'm not going to say much more about this. The complexity in this relatively simple form is more than I can elaborate right now. But I've just asked you to look at the very last bullet here, because what it does is, again, it focuses change from choice of inferential procedure to model development that achieves satisfying integration of knowledge. That's what it's all about. No longer are you constrained, by inferential procedure. Now you just can be liberated to build models that capture the process, the features of the process that you are interested in. So that's why, in some sense, this is so beautiful, it's so elegant. Obviously, I am pontificating a little bit here, and I do that a lot. But anyway, so this also came with the change in the data collection landscape. In the 60s, 70s, 80s, even earlier, most data was collected with experimental designs. People would design an experiment and go collect data under that design. What happened as we moved into the 21st century is people started looking at observational data. This is what you really observe about the process. The difficulty with experimental designs is that it kind of limits your ability to see the process because it constrains what the data can look like because of the design. And so therefore you cannot do as much with experimentally designed data as you can do with data from just plain observation. And so that really, again, has had a dramatic impact on how we look at analysis. I have to put in one slide here on machine learning, since everybody hears the word ML, machine learning. And so I just write here nothing more than the fact that machine learning is a tool that, enables you to do a lot of things very fast, get a lot of quick inference very quickly, but it may not be as satisfying as you'd like it to be. And in particular, what happened after a little while was probabilistic machine learning came along because plain old machine learning was too deterministic, didn't capture any uncertainty. And so probabilistic machine learning came along, and that's essentially Bayesian inference. And again, I'm not going to get into any details about that, but for example, deep learning is an example of a Bayesian algorithm, and many of you may have heard of deep learning. I have one last slide here before I say something about spatial statistics. This is, for me, what we call a soapbox, where I have to express my concerns. The rapid rise of data science leads to trying to put statistics under the same umbrella as things like information science and computer science. And while it is certainly true that statistics supports data science, I think statistics has to stand alone. It has to stand alone because rather than putting algorithms at big data sets, what statistics wants to do is offer the opportunity for careful modeling of complex processes, careful thinking about what's going on. And also, not all data sets involve terabytes of data. There are lots of situations, particularly, for example, in the collection of environmental and ecological data, where the data sets are not huge, but the problems are really challenging. And I'm just going to insist that there has to be space for thoughtful investigation of processes where the data is usually inadequate and usually not enormous. Okay? So last few slides on spatial analysis. I'll put you out of your misery in about 3 minutes. So just hang on a little bit longer, please. I've been excited about spatial analysis for 30 years now. I was there at a good time. What we're concerned with here is a lot of times spatial data is collected with spatial referencing. In other words, locations in geocoordinates or locations in terms of areas, and so data has some spatial referencing, and if it does, it's not good to just ignore it. It's not good to ignore it. If you bring it into the modeling, if you take advantage of it as information, you will improve your inference about what you are studying. And so my point really is that that's what I'm trying to argue is the real value of thinking about spatial data. Okay, and so I was fortunate. I joined the spatial world at a time when essentially in the Bayesian community there was nothing. There was nothing. It was empty. Opportunity was enormous, and I jumped right in, and I was very fortunate, but it worked for me. And without saying much more, I would only say that specifically for spatial data, Bayesian inference is much better than classical inference because it doesn't require any asymptotics, whereas spatial data has to force you to think about what sort of large sample data might mean. Is it a bigger region? Is it more points in a given region? What does asymptopia mean for spatial data? Whereas from a Bayesian point of view, inference is exact, uncertainty is perfect, and you just, whatever model you specify, that's what you can learn. So, that's my niche in this community. I argue here that a lot of spatial data is inadequate. My colleagues here will know that I complain all the time that the data is inadequate, and my colleagues in other research groups that I'm involved with also will hear me complain all the time. But what this only forces you to do is become more and more knowledgeable about the science, more and more aware of what data is needed to answer the questions. And so altogether it becomes collaborative, and what I really like about it is I can feel green. I work on environmental problems, ecological problems, and being green, not so bad, not so bad. Last thing is I'm just going to show you a couple of pictures of some spatial data, just so you get some flavor of what these things might look like. So here is one type of spatial data. Here's a bunch of monitoring stations, and they're collecting particulate matter, which is a pollutant that results from various sorts of emission sources. But in any event, all I show here is for 3 states, in Illinois, Indiana, and Ohio. You can see locations where monitors were placed, and you can see the pollution levels that are collected at those locations, and you can see the spatial variation. The second one is aerial data. So here the US is partitioned into states, and you can see here that we're collecting average test scores for each state. And again, you can see spatial pattern. Elevated scores clearly occur in the middle of the country. There's an explanation, but not for now. And here's the last type of spatial data, which are the points themselves being random. The points are random, and all that means is that we get a point pattern of observations. And this is looking at 7 different invasive species, and you can see the point pattern of their locations in New England, in the US, and clearly there's a lot of difference in the point patterns according to the species. So I stop. Thank you so much for listening.
you so much, dear Dr. Gelfand, for your excellent conference. We met like 1 hour ago, and he told me, you can do it in Spanish. It's okay for me. I can understand very well. So then we are going to do my talk in Spanish, but please, if you can understand anything, yes. Familiares de nuestro homenajeado, padrinos, señoras, señores, he de decir que es un honor para mí, se lo he dicho al homenajeado ya hace un ratito, pero es así, es realmente un honor. Como rectora de esta universidad, presidir este acto en el que otorgamos nuestro más alto reconocimiento al estadístico don Alan Gelfand. La investidura como doctor honoris causa es una de las ceremonias más significativas y emotivas, a su vez, de la Universidad de Zaragoza. Hoy rendimos homenaje a un profesional muy destacado en el ámbito de la estadística, con una trayectoria profesional brillante y con un vínculo muy estrecho, afortunadamente, con nuestra querida universidad. En primer lugar, quiero destacar los valores que encarna el profesor Gelfand, quien, al margen de sus indiscutibles méritos profesionales, encarna perfectamente nuestros valores universitarios de búsqueda de la excelencia, de compromiso, de trabajo y de responsabilidad con nuestra sociedad. Alan Gelfand, quien hoy está acompañado por sus padrinos, los profesores, doctores don Gerardo Sanz Saiz y doña Ana Carmen Cebrián Guajardo, es una figura influyente en la estadística moderna y un pionero en la cuantificación de la incertidumbre, que, por cierto, cuántos dolores de cabeza nos da. Su nombramiento como doctor honoris causa reconoce su excepcional trayectoria en el desarrollo y aplicación de los métodos bayesianos, un enfoque que combina datos, como él nos decía, y modelos probabilísticos precisamente para cuantificar la incertidumbre. Las contribuciones científicas del profesor Gelfand en el campo de las matemáticas y de la estadística acreditan su liderazgo mundial en el desarrollo de estos métodos. Su intachable trayectoria incluye 33 años como profesor de la Universidad de Connecticut, un traslado posterior a la Universidad de Duke y estancias como profesor visitante en prestigiosas universidades como Harvard, Sydney, Washington o Nottingham, entre otras. Además, su vínculo con universidades españolas y con la Universidad de Zaragoza se extiende ya por varios años. Gracias, profesor Gelfand, por sus contribuciones tan sustanciales en la estadística bayesiana, espacios y la modelización jerárquica. Estas contribuciones han revolucionado, sin duda, el análisis de algo tan importante hoy en día como son los datos, haciendo que problemas que antes eran imposibles de resolver en la práctica, ahora se conviertan en problemas tratables. Profesor Gelfand ha sido merecedor de prestigiosos premios y distinciones en el ámbito de las matemáticas y de la estadística, unos reconocimientos a los que hoy sumamos nuestra elevada distinción como doctor honoris causa de la Universidad de Zaragoza. La vinculación del profesor Gelfand con nuestra institución viene de lejos. Colabora con la Universidad de Zaragoza desde el año 2012. Por lo que quiero agradecer también, porque si usted está aquí hoy en parte, es por la labor y el trabajo de todos esos profesionales de la Universidad de Zaragoza que le han atraído a nuestras aulas y a nuestros laboratorios. Quiero agradecer por eso al Departamento de Métodos Estadísticos, al Departamento de Economía Aplicada y al Instituto Universitario de Matemáticas y Aplicaciones, IUMA, su iniciativa en la propuesta de este nombramiento, que fue el primer paso para que hoy estemos aquí, reconociendo la trayectoria del profesor Gelfand. Y además, profesor Gelfand, he de decir que tiene usted a su alrededor mucha gente joven que está iniciando o que lleva no mucho tiempo, como otros que estamos sentados aquí, en el mundo investigador y académico, ¿no? Es tremendamente positivo el ver a una persona como usted, de esa altura científica, que me atrevo a decir a nivel mundial, aquí, en nuestra casa, en nuestras aulas, interaccionando con ellos. Ya lo ha hecho estos días, me consta que ha habido un seminario, pero lo va a seguir haciendo porque después del Honoris. Y esas semillas que usted va a sembrar en nuestros jóvenes, seguro que tendrán su fruto. Con lo cual, gracias por inspirarnos a los no tan jóvenes, pero sobre todo a ellos. Ellos son el futuro y de verdad que espero que esas semillas florezcan cuanto antes en nuestra gente de la Universidad de Zaragoza. Porque lo que usted ha hecho es muy universal, nos llega hasta los biomédicos. Los biomédicos trabajamos continuamente con esos métodos estadísticos y no solamente los biomédicos. La ciencia pasa por la estadística, con lo cual son métodos tremendamente universales que nos llegan a muchos de los profesores y los investigadores de todo el mundo. Para terminar, me gustaría hacer referencia a la importancia del trabajo científico hoy en día y la transferencia de ese conocimiento a la sociedad. Contribuciones como las suyas nos ayudan a solucionar problemas, abriendo un camino de posibilidades que hasta ahora desconocíamos. Para eso sirve la ciencia, para eso sirve la investigación, para avanzar en nuestro conocimiento y trasladar estos avances a nuestra sociedad. Muchas gracias de corazón, doctor Gelfand, por su dedicación, por su manera de hacer ciencia que combina, a mi juicio, la genialidad, trabajo en equipo e ilusión siempre por comprender el mundo. Bienvenido a la Universidad de Zaragoza y recuerde siempre que esta ya es su casa. Muchísimas gracias. Pongámonos en pie para entonar el Gaudeamus Igitur, himno universitario. Muchas gracias a nuestro coro que nos acompaña en el día de hoy. Gracias y en nombre de toda la comunidad universitaria agradecemos vuestra asistencia y participación. Están todos ustedes invitados al aperitivo que se va a realizar en la sala Josefa Amari Borbón. Queda clausurado el acto, no sin antes transmitirles que pueden aprovechar el paso por este edificio para ver una exposición que tenemos muy singular en la planta baja sobre teatro y pintura del Renacimiento. Muchísimas gracias y disfruten del aperitivo.
Prileti la, lašti voška, stala sobi,